Good morning, everybody. Welcome to Tippett's Physics. What is crappin'? Today we're going to look at potential energy, a specific type of energy, and specifically we're going to look at a subcomponent of potential, and that's elastic and gravitational. Really quick, on the previous lesson we looked at mechanical energy, and we said that mechanical energy is energy due to the position or motion of an object. And for this lesson, we're going to look at energy that's due to the position of an object. And the first one is elastic potential energy. Elastic potential energy. If you've learned before, potential energy is energy that is stored. Stored energy. And that means it's energy that's available to be used, so it's not currently being used at the moment, but it has the potential to be used. So elastic potential energy, that's energy that's stored in a spring. Energy that's stored in a spring. And its units, it's the same units as work. Its units are joules, capital J. And we already looked at this formula beforehand in physics when we were looking at impulse and momentum for our egg drops. But we'll write it down now. Potential energy. Oops, I meant to do a different color. Sorry. Potential energy in a spring, so Pe sub S, is equal to 1/2 kx squared. And we looked at all these variables before. K is the spring constant, and x is the elongation of the spring from beginning to end. Or sorry, the change in elongation. So let's just look at a quick example. When we look at, if you imagine that you have a bow and arrow. Let's see if my drawing works for this. Okay, that's our bow and arrow. And you are pulling back the elastic string on it. So in order to pull it back, you're applying a force on it, and it's moving a distance. Your hands are, I think, you have really long hands for this. One thing is holding on to the bow, that's hand one, and the other hand is pulling back on here. Stretch Armstrong. Anyways, you're applying a force, and it's moving a distance. Do we remember what that's called when you apply a force over a distance? That's called work. So you're doing work on the spring, and you're giving it potential energy. Imagine you have a rubber band, you're getting ready to fling it at somebody. So the further you stretch it back, the more energy it has and the harder it's going to hurt, the more it's going to hurt. So by doing work, we're giving it energy. Okay, so let's do a quick example together. A spring with a spring constant of 4.0 newtons per meter, that's K, is compressed by a force of 1.2 newtons, that's a spring force Fs. What is the total elastic potential energy stored in the compressed spring? So we're looking for Pe sub S. So let's write down our formula first. Pes is equal to 1/2 kx squared. And we're solving for Pe sub S. Notice we don't know what x is, how much it stretches, or how much it's compressed. So what we need to do is use the force to help us find that. And we know from the previous unit that the force on the spring is equal to kx. Oops. Kx. So let's solve for x. X is equal to Fs over K. Plug and chug, 1.2 newtons over 4.0 newtons per meter. And that gives us an elongation of 0.3 meters. So now that we know what X is, we could plug that in and solve for the potential energy. So we got PE sub S is equal to 1/2 K 4.0 Newton meters still, newtons per meter, times X 0.3 meters, quantity squared. Plug and chug, and we get in our calculator 0.18 joules. The next type of energy we're going to look at, potential energy, is gravitational potential energy. I'm just going to use PE for short, gravitational potential energy. And this is the energy that's stored due to the position of an object. So energy stored due to the position of an object. And by position we mean height, so how high is it relative to what's below it? Height of an object. In order to get that object to a certain height, we have to do work on it. So we're going back to work, and remember, work is equal to force times distance. So if you want to lift an object up in the air, you're going to give it potential energy, and when you drop it, it's going to use that potential energy. So in order to lift it up to the air, we have to do work against gravity. Remember, that's Fg, and we're lifting at a certain height, d. If we expand Fg, Fg is mg, so we're left with mg. And instead of using distance, we're going to use height, so we know how high it is above the ground. And that is equal to our potential energy, our gravitational potential energy. So in order to get the potential energy, again, you have to apply work to get it there. Now, it's always relative to the position of the object. So let's say we have a desk or a table, and you want to lift the ball from the bottom up to the top. If you were to let go at the top of it, so it falls to the floor, the potential energy would be based on its change in height from here to here. However, if you slid over a little bit to the table, and you're a few inches above the table, I suppose, the potential energy is now based off of how high it is relative to the table. So the height is from the bottom to the top of the two positions you're looking at. So let's look at an example of gravitational potential energy. Alright, so let's look at this example. A 0.06 kilogram egg is dropped from the third floor of the stairwell. How much gravitational potential energy does it have at the top of the stairwell relative to the bottom of the stairwell? AKA, the height is 30 meters. Now, really quick, this happened in physics class the other day where a student dropped an egg from the top of the stairwell, and I was at the bottom recording it to get a nice action shot, and all of a sudden the egg hits the stairwell, and obviously it explodes. And then all the yolk starts spilling all over me. It goes from my head all over my shirt. And now I've got a stained shirt with flies flying around it all day long. And I am absolutely livid with a student. And I'm fantasizing about all these mean things I'm going to say about the stained shirt that I have. So I go upstairs and I'm huffing and puffing. And I see the student. And all of a sudden I turn into a little worm. And I ask, what kind of egg was that you dropped? Was it a double A, or was it a large or an extra large? Was it farm fresh, or was it from the store? And story of my life, I always cower, I guess, in the heat of the moment. Anyways, let's look at this egg. So, we've got the mass, 0.06 kilograms. And we know the height is 30 meters. We want to know how much gravitational potential energy this egg has at the top. So our formula, PE, is equal to mgh. In this case, g is the acceleration due to gravity. So the potential energy, just plug in chug, 0.06 kilograms times 9.81 meters per second squared times 30 meters. And we get for our potential energy 17.7 joules. Now if we want, we can look at how much potential energy this has from the top floor to like the first floor. So what we'd have to do is look at the height. And instead of 30 meters, if it goes from the top, the third floor, to the first floor, the change in height would go from 30 to 10. So PEG is equal to still the mass, 0.06 kilograms, times 9.81 meters per second squared. And again, this time we're going from 30 meters, the third floor, to 10 meters, the second floor. So the change in height would be 20 meters. And we plug that in our calculators, and this time we get a little bit less, 11.8 joules. And that's it for today. Fortunately, the shirt that the egg yolk landed, was a collared shirt, and obviously it stained my shirt, but at least now I could wear it under my sweaters, and nobody will see the stain. That's it for me. See you next time.